I'll hand over to Michal Bílek for the last talk of today.
Okay, thank you very much, Indra, for introducing me and the organizing committee for giving me the opportunity to speak here. So the strongest indication of MOND probably comes from its ability to model the rotation curves of galaxies. Nevertheless, this is not convincing for everyone. There are people who say that this is the same can be done with a suitable distribution of dark matter with Newtonian gravity. We know it's not that easy in the real simulations. Nevertheless, it would be nice to have additional discriminator tests that are independent of this. There are indeed phenomena that are expected to come out differently with Newtonian gravity as with MOND. Nevertheless, here I'm going to speak only about tests of modified gravity MOND, namely these two formulations using dynamical friction. So first I will recall what is dynamical friction. So imagine that we have a massive body called a perturber that moves through a sea of much lighter particles. Here we can imagine a satellite galaxy or a globular cluster that moves through stars or dark matter halo of its host galaxy. The trajectories of these light particles are bended by gravitation such that they create an overdensity behind the perturber, and this overdensity acts by gravity on the perturber and decrease its velocity. In Newtonian gravity, we have a way to estimate the strength of this force. This is given by this Chandrasekhar formula. Here n stands for the mass of the perturber, rho for the density of environment of the medium at the position of the perturber, v for the relative velocity of the perturber with respect to the medium, and sigma for the velocity dispersion of the medium. This logarithm lambda is the so-called Coulomb logarithm. It depends on the concrete geometric configuration of the system under consideration, but it is expected to be of the order of a few. We know that Chandrasekhar formula works well in some cases, but in some cases it breaks down. Dynamical friction in MOND is less explored, but there seem to be two regimes. If we have interaction of two objects with comparable masses, such as some major merger of galaxies, then dynamical friction is weaker in MOND than in the equivalent Newtonian system. The equivalent Newtonian system means that the distribution of baryons is the same as in MOND, and the distribution of dark matter is such that the gravitational field predicted by MOND is reproduced. And because of this reason, we think that major or intermediate galaxy mergers are rare. When two galaxies interact, they can just fly around each other and never meet them again. This seems to be good because it can explain some long-standing problems of galaxy formation that people had with Newtonian gravity, for example, the formation of bulgeless galaxies, or to explain the fast rotation of galactic bars. On the other hand, if the perturber is small with respect to the whole system, which is the case, for example, of globular clusters in galaxies, then dynamical friction is expected to be stronger in MOND than in the equivalent Newtonian system. This is a result that comes from analytic calculations. It was found that the ratio of dynamical friction timescales between MOND and the equivalent Newtonian system is proportional to this factor. Moreover, there has been proposed the MOND analog of Chandrasekhar formula, the so-called Salcedo formula, but this formula has not even been derived in a proper mathematical way, and it has not been tested by simulations before I worked, so it was not completely clear. People just took this factor and multiplied this Newtonian expression and said that this is the formula for dynamical friction in MOND. So if we apply this factor to low mass, low surface brightness galaxies, this means the dwarf galaxies or ultra-diffuse galaxies, we will find that the enhancement of dynamical friction can be extreme compared to Newtonian gravity. If this can be for dwarf galaxies something like 1/10, and here this is to the second power. So as a result, globular clusters were predicted to sink in the centers of their host galaxies. Here I mean the dwarf galaxies on the time scale of 1 gigayear, which is less than the ages of globular cluster systems that are derived from the models of stellar evolution. So does this mean that MOND is excluded? So this question has been raised up already in 2004. It didn't receive much attention, but I recall it when this object was discovered. This is the DF2 galaxy. It is an ultra-diffuse galaxy, which means that it has a mass of a dwarf galaxy, but a radius of the Milky Way, which makes it a very low surface brightness object. The enhancement of dynamical friction should be large. And moreover, this galaxy has very massive globular clusters, 10 to the 6 solar, which is 10 or 100 times more massive than the typical globular clusters that, for example, Milky Way has, which would call additional enhancement of dynamical friction through this term, if the Sanchez-Salcedo formula is correct. So when I saw this, I thought, oh, can the observations of such objects really exclude MOND? So we decided to make the simulations to verify the analytic results. We used phantom of Ramses, a solver of gravitational field for the Q-MOND version of MOND. We simulated the galaxy to resemble the DF2 galaxy. The simulation had a relatively high resolution, 20 solar masses per particle, and spatial resolution 50 parsecs. The globular cluster was modeled as a point mass. First, we tried simply to put the globular cluster 5 kiloparsecs from the center of the galaxy, so something more than 2 effective radii, and let it freely fall on the center of the galaxy from rest. So here we see the distance between the globular cluster and the center of the galaxy as a function of time. First, we see here these damped oscillations, but once the globular cluster reaches the inner kiloparsec of the galaxy, something strange happens. Dynamical friction suddenly becomes much less effective. First, we suspected whether this could be because of insufficient resolution of the simulation, but it doesn't seem to be the case, because the spatial resolution was something like 10 times better than the radius where this starts happening. We tried to increase the numerical resolution, and we got the same result, just in a longer computational time. And finally, we had a look in literature, and we found that a similar effect has been already reported for Newtonian gravity. It is called core stalling, and it is known to happen in gravitational potentials, which behave like the radius to the second power. So the globular cluster of this mass never completely settles in the center of the galaxy as a result. Then we decided to test the Sanchez-Salcedo formula, the MOND analog of the famous Chandrasekhar formula. We repeated the previous simulation with the free fall of the globular cluster, but for different masses of the globular cluster. The orange line stands for the integration of the analytic formula, and the blue curve was extracted from simulations. And we see that the two agree well, with the exception of the inner 1 kiloparsec of the galaxy. So the Sanchez-Salcedo formula is not able to capture the core stalling phase. This is the same as for Newtonian simulations, where Chandrasekhar formula doesn't capture core stalling because of the simplifications that were done during the derivation of the formula. Here we try to do the same, but for different eccentricities of the orbit of the globular cluster, and again, the Sanchez-Salcedo formula works quite well with the exception of the center of the galaxy. The real DF2 galaxy contains 10 globular clusters, so we made a simulation with a initial distribution similar to that we observe in the galaxy, and we can see that the outer globular clusters, they don't experience much dynamical friction while the inner do, which leads to a modification of the distribution of the globular cluster system. The system becomes more cuspy, more concentrated, and here we predicted how it should evolve with time with two globular cluster mass functions. First for the globular cluster mass functions of very massive globular clusters observed in DF2, and here for the standard globular cluster mass function. And in the future, it will hopefully be possible to compare this to observations. We just need to observe more isolated, ultra-diffuse galaxies than we know now. So this was for the case of so here this refers to simulations only with a spherical n-body galaxy with no hydrodynamics. We are currently working on the case of globular clusters of isolated dwarf galaxies. These differ from the objects that we simulated before because they are these galaxies rotating. They are gas-rich objects containing 50 or even 90% of their baryonic material in the form of gas. Moreover, they are smaller and lighter than the UDGs that we investigated before. So the first thing we did was to have a look what isolated dwarf galaxies contain globular clusters from the observational point of view. So here we see the baryonic mass of the galaxy, and here the number of globular clusters. So globular clusters start to be common at the mass of 10 to the 8th power, and there are some globular clusters in galaxies of the mass of 2 times 10 to the 7th. Here we see that the radius, the projected distance of a globular cluster from the galaxy center over the effective radius is usually less than 1. And here is just a scaling correlation between the effective radius and the baryonic mass. So we set up the simulations accordingly. We simulated either the mass 10 to the 8 or 0.2 10 to the 8 solar masses. We started with 90% of gas, such that well, we start with what we think was the state of the galaxy at the redshift of 2 when globular clusters were typically formed, and the size and mass of the galaxy was chosen according to simulations, according to observations. And first I'm going to show you results of simulations of the clusters of the mass 10 to the 5 solar masses, which is still a relatively typical mass of a globular cluster. Here we see a globular cluster that orbits in the plane of the disk of the galaxy in the same direction as the galaxy rotates, and we can see that there is no core stalling. The cluster settles in the center of the galaxy in 2 gigayears. Nevertheless, if we put the globular cluster on the retrograde orbit, we will see different behavior. We will not see it. So it is running, but it is almost the end of the simulation. But if you have noticed, there was almost no dynamical friction for the retrograde case. So does this mean that we cannot observe globular clusters on prograde orbits in real dwarf galaxies? It's actually not the case. because these simulations ignored one important fact, and this is the gas-rich galaxies form stars. So here, in this simulation, the globular cluster was initially on a prograde orbit that initially was sinking quickly. With supernova explosions, we see a different picture. The bubbles of supernovae cause large variations in the total density of the galaxy. There is no dark matter. These cause large variation in the gravitational field, and these make random pushes to the globular cluster such that the cluster cannot settle at any particular place of the galaxy. And this works as long as there are any supernova explosions, such that the cluster can survive out of the center of the galaxy for 10 gigayears. Of course, the usual problem with such simulations is that we don't know how to set the star formation parameters correctly and how to set the supernova parameters. So we tried many different combinations, and so these are those different lines. But it turns out that as long as there are supernovae, the cluster never settles. We tried a simulation in an equivalent Newtonian system. This is this dashed line, and it confirmed just the analytic results. Dynamical friction is much weaker in this equivalent Newtonian system than in the MOND system. Then we changed the mass of the globular cluster to be 10 times less than before, and such galaxy has no problem to survive in the galaxy even without supernovae. So finally, I will show you very preliminary work on the Fornax dwarf galaxy. I have just started working on it. So the next step in this program is to investigate the survivability of globular clusters in non-isolated galaxies where the external field effect might play a role. So this is the satellite of the Milky Way, and there is measurement of its proper motion. So I integrated its orbit backward in time, and it turned out that the galaxy moves on a highly eccentric orbit, and even in percenter, the value of the external field is quite low. It is just 0.5 of the internal value, such that the effect of the external field is quite low. So I made a simulation of the galaxy in isolation. The globular clusters, there were 5 globular clusters. They were modeled as resolved many-body objects, and in this case, no miracle happens. The globular clusters sink in 3 gigayears, so there is no core stalling. So what does it mean? Well, you can give me your suggestion. So maybe we need to change some of the free parameters of the problems, such as the mass-to-weight ratio, the mass of the Milky Way, or to assume that the real proper motion is several sigma, different from the measurement. But it seems that this adjustment will have to be quite large, so it's not a very elegant solution. Or maybe we have to do the same as people suggested for this galaxy in the Newtonian framework. The survivability of globular clusters is problematic even in Newtonian gravity, and it has been proposed that the Fornax dwarf is actually a merger, is a remnant of a recent merger, such that the globular clusters did not have time to settle in the center of the galaxy. I still need to study this paper, but they see that they say that they see some evidence for this, or maybe our results indicate that we actually need a different MOND theory than QMOND that was employed in the simulations. So here is my summary, and I think that I'm done.
So Just before you take questions, I want to mention in the Fornax case, there was a paper pointing out that the globular clusters might be a little bit in front or behind, because you only mentioned the projective separation.
Yes, yes, yes.
So if they were a little bit further away from the cluster, would that be suggestion?
No, so it would make the thinking time to be longer.
Yeah.
So it depends how far in front or behind they are. But really, do we have a way to tell how far the globular cluster is? Are the measurements precise enough? Really, I cannot say.
Probably not. So one would have to use a statistical argument, right? How much line of sight depth distance would be reasonable. Right. Are there any questions? Yeah.
So basically your simulations tell us, even if we accept them as correct, that what will happen in the next 3 gigayears. Right?
Yes.
But how do we know, starting from today? So
Yeah, that's a good point.
The
Yeah.
question is, you could have started with
Yeah, so it is really...
Maybe it had 10 globular clusters and 5 of them already sank or whatever.
Yes, yes.
I think it's just technical. When you said that the external field at Clarion passage is half, you mean half the internal one?
Yes.
You mean in fornax or the fornax globular cluster internal acceleration?
So this...
Which is smaller one.
Mm,
What is G internal?
G internal, if I remember well. So I calculated
Not
the
the number.
profile.
What is it? Is it what?
Inside Fornax.
Inside fornax?
Yes, so this external,
Yeah,
this is just in the center of the galaxy, and this internal, I think that I calculated the profile of acceleration within the whole volume of the galaxy, and this is the maximum value.
Sorry, G refers to intergravity of the globular cluster.
Exactly.
No, of the whole galaxy.
Of Fornax.
Yes, of Fornax.
Right.
Yeah, but you should have calculated the effect, of course. Take the internal acceleration of fornax cluster. Right? Suppose it is a bit faster. But also I would say, okay, it could still have an effect every time you go, because it must have, in 3 gigayears, it made many passages. What is the orbital period of fornax?
So I think that there are something like 4 orbits in the last 10 gigayears.
But every time it passes, something will happen to the system, right? Do something.
It does. But when I calculated the change of the internal acceleration because of this change of external field effect, the change of acceleration was just a few percent, maybe 10% at most. So I used this Freundlich formula for this. Maybe another formula would give another result.
But the orbit of fornax is not part of the simulation.
No, this is just when I calculated. Oh, this is just.
Position. This is present external.
So no, this is not present. This is not present. So this is at very center. I just integrated the orbit backward in time.
Get the speaker on.
Right. So yes, this is calculated at Paris Center. So just to recap, when you were doing these simulations, you don't include the way around the Milky Way.
So when I do the simulation, the self-consistent simulation,
Yeah.
it is done in isolation.
And you think that should be reasonable because the external field for the Milky Way is relatively modest.
Yes, so this was
Okay.
that was the argument.
So do we have Oliver at the back?
Very interesting work. So in 2022, Fabian et al. Published a paper on nuclear star clusters in star-forming dwarf galaxies, so in the range of 10 to the power 7 to the 10 to the power 9. And the nuclear star clusters were basically at rest compared to the velocity of the dwarf galaxies. So it looks like they are not kicked around. What do you take from these observations which are out there?
So you are speaking about the relative velocity of the cluster with respect to the stars.
With respect to the stars and the gas, both.
But all of these tracers move in the same gravitational potential. I think that all of them move together when they feel the same gravitational field. So if the globular cluster is kicked, then the stars are kicked in the same direction. So maybe, I don't have a simulation of this, but I would guess that the effect of the variations of potential would be very similar, both to the cluster and both to the star, such that we will not see their relative motions.
Okay, could you extend that to your simulations basically to stars and gas and really see that they do the same? Could you extend that?
It is a good idea. It might be difficult from the technical point of view, but I think it's doable. I don't have it at the moment, but it is an interesting thing to check. So maybe you send me the reference to this paper.
Well, dynamical friction is something that depends not only on the density, on the local density, but also on the distribution function of the particles doing the friction. And in this case, of course, the particles doing the friction are just the stars. And that's why you see a difference between, in the disky bit, co-rotating and counter-rotating disks. So the dynamical friction problem we are trying to solve here is going to depend also sensitively on the anisotropy parameter and the which you assume whatever anisotropy you assume for the stars in Fornax, and for any radial variations in the anisotropy. So I was just wondering, you didn't mention what that anisotropy profile was. I wonder if you could have you changed it?
Parameter 0.
So you took isotropic.
Yes.
But we know the stars in this galaxies are not moving isotropically.
Do you have a reference for this?
Yes.
Oh, okay, just send it to me. I would be interested. It wouldn't be that difficult to implement it in the simulation.
Towards the center, they tend to be more isotropic orbits, but towards when you go towards larger distances, they tend to be radial anisotropies. And if you have a radial anisotropy, well, I can't think of the top of my head, but I have to think a bit. But certainly, the dynamical friction problem is going to be a little difficult, a little different than if you assume isotropic orbits.
I agree with this, that maybe there is a difference, even though I don't expect that it would change the Globular cluster thinking time from 3 gigayears to maybe 20.
Well, yeah, why 20?
It needs to be longer than 10.
Yeah, a factor of 3 because the anisotropy changes.
I can try. So really I work on this just for something like a day. So these are very preliminary results.
It should be relatively easy to change the anisotropy parameter.
Yes, it is.
Michal, Fornax is a special type of pure spheroidals because the star formation history that can be measured by looking at the core magnitude diagram indicates that it has been forming stars with a constant roughly rate for 10-11 gigayears, and then essentially stopped forming stars just alpha gigayear ago. So for most of its lifetime, it had a significant ISM, for sure, and I was wondering whether this can change somehow your conclusions.
So if it was forming stars, this means that there was gas probably, and in that case, we would be, in this case, in the perturbations by supernova explosions. So yes, it would be a reason, a way to extend the lifetime of globular clusters.
Not only you get gas, but most of the stars today are not there. It was
As well.
form of gas. It would be less friction.
Well, there's also friction against the gas.
Yes, gas is a source of friction.
In principle, the star formation history is available in the literature, so we could also use that as an input for
In principle,
a simulation that actually follow the history of the object.
implementation of this in simulations is more difficult, but it's good to know that these observations are here. And
Hi, it's really nice work, as Zaida Lieber. So I had a question about also the implementation of the dynamical friction in MOND, because all the orbit, or almost all the orbits that you were showing were really radial, because it was free-falling objects. So all
some of them, not all. So I can show. So this first is radio, these are radio, these are not radio. Some of them are circular or simply eccentric.
Okay. Because in the classical Chandrasekhar formulations, you have a lot of dependency of the Coulomb parameters in Newtonian dynamic. And I was wondering if in the formulation that you have in Sanchez-Salcedo, you had something similar to adjust.
Yes, exactly. So Sanchez-Salcedo formula is just the Chandrasekhar formula multiplied by this term. So we still have the Coulomb logarithm, and here, in order to get the match between the simulation and the analytic formula, I didn't mention it, but to get a good match, you need to tune the Coulomb logarithm. This is the same as with the Chandrasekhar formula in Newtonian gravity, and we generally got that more circular orbits require a higher value of Coulomb logarithm, and this is qualitatively similar to what has been found for Newtonian simulations.
So maybe just one more quick question. We'll let Q.
I have a basic question. Since you are testing with some time scale, I wonder whether you did or you have to do this simulation with the formation of galaxy itself. I mean, is the formation of this ultra-diffuse galaxy is very interesting.
So the ultra-diffuse galaxy, we just didn't include any star formation. It was just done at the beginning, and it was complete. And I think that for this galaxy, it is actually what is observed. The edges of the globular clusters are the same as the edges of the stars of the galaxy. Seems that all of this formed together.
I mean, I wonder whether you are assuming the galaxy is stable for, say, 10 gigayears.
Yes, it is stable. There are no interactions with anything external.
I have a little knowledge, maybe someone can tell. I mean, do you understand how these ultra-diffuse galaxies form and grow for over 10 years?
I think nobody knows.
Then
So there are suggestions, but I think that people didn't converge to any scenario, and people usually work within the lambda CDM scenario, which would not apply to MOND to the MOND universe that we are speaking about here. So, right. So it is something to consider for the future. That's for sure.
Did you have a quick question?
Maybe in Fornax case, there are 5 massive globular clusters. The most massive one is about 10 to the 6. 10 to the 6. They add up about a few 10 to the 6 solar masses. Comparable to, start to be comparable to the core of the stellar core of, not equal to, but in that.
It depends on your definition of the core of the galaxy.
The Plummer core.
So Plummer. So actually, for the simulation, we used a star-shaped sphere. So this is the latest observations that I found were described by a star-shaped sphere.
Yeah, what's the
so
index?
I used this one.
What's the index of a star-shaped?
Probably a low index, something like 1. Probably a low index, something like 1 or
1 means actually a cusp. Star-shaped index 1, I think, means a cusp, but which means they can go in. They don't have a core.
Yes.
Yes,
they don't have a core. So this is why this core stalling doesn't work here.
Just to understand that. Just make sure I understand it.
All right, so I think we've had enough questions for this talk. So I'd like to thank the speakers for the afternoon session.